Oh, one other thing here, even though I haven't mentioned it before apparently, I do want to bring up, if you try to decide which slit that it goes through, that ringing a bell? What happens?
It doesn't behave how you expect it would behave.
And how does it behave?
It goes, it's like two.
Yeah. So you put a detector in there to see which slit it goes through. You're treating it like a particle. It behaves like a particle. And so you get just the two bumps. Okay. So we start out with how do you find speed? Flashback, probably the first week of Physics 251.
Distance traveled over time.
Yeah. So distance over time. And in terms of momentum, what is, I guess, velocity? I'm going back and forth between scalars and vectors here. It's going in one direction. So in terms of momentum,
Momentum over mass.
yeah. And so we have this relationship here. Let's see, the version I want it in is time. So delta t, this change in time, is equal to m delta x over p. And I was doing this earlier today. I kept leaving off that subscript. We're talking about motion in the x direction. All the p's should be p sub x. All right, so we're going to put that on hold for just a moment while we do something else, and then we'll come back to it. Frequency, I know, is speed over wavelength. And wavelength is, yeah, V. Wanted to throw a C in there, but we're not talking about light. We're talking about particles, or traditional particles. I know that the wavelength, well, we bring in the de Broglie wavelength, which is h divided by p. And speed is p divided by mass. Making sure I'm going in the right direction here. So we end up with p squared over hm. Ooh, I know. True story. So therefore, the FTP equals
px over h2.
so df is equal to 2px h dot m dp. I know that so if I think about this in macroscopic, again, hand waves, that I find unsettling, but it's sort of necessary to get there. So the change in frequency, it times the change in time is, well, my change in frequency, 2px over hm delta p. Change in time, we have that one, that is m delta x over px. Get rid of some stuff, we get rid of the m, get rid of px, and we're left with 2 over h delta p delta x. Another hand wave coming in here. What's the relationship between frequency and period?
Frequency is 1 over period.
Yeah. So if we're talking about a single wave, that time that it would take to produce that wave is the period. So this is just crudely equal to 1. And so we end up with delta p delta x is equal to h over 2. Again, it's a pseudo derivation. And then one last final hand wave, or 2, depends on how you want to count it. Delta p delta x is less than or equal to h bar over 2. It's greater than or equal to. So the derivation, I've seen several textbooks go into the pseudo derivation, which is what I basically presented to you. It's very difficult to find the h bar over 2 derivation. But that's why that last massive hand wave. But what this is saying is that I've got these two quantities. I have momentum and I have position. And the more I know of one, the less I'm going to know of the other. That if I look at the uncertainty in each of them, that I know that the product of that uncertainty has got to be greater than or equal to this constant right here. That it is impossible to find out more detail. I cannot know the momentum and the position at the same time. Just like with wavelength and the position that we had earlier. This leads to the physics joke. Schrodinger and Heisenberg are going down the road. Heisenberg's driving, gets pulled over by a police officer. Heisenberg rolls down the window. The police officer says, "Do you know how fast you're going?" He goes, "No, but I know where I am." Then, as we will get to, the policeman says, "Well, you open up the trunk." They open up the trunk, and he says, "Did you know you have a dead cat in here?" And Schrodinger goes, "Well, now we do." If you don't understand that, we will explain that in a moment. Like all physics humor, the laughter is on the inside. All right, so we were left with this idea of there's definitely uncertainty in how we can do measurements. There is also an issue with the fact that still, how do we describe particles in waves? So Schrodinger came up with the wave function. Pretty sure that was Schrodinger. There was Heisenberg, Dirac, and Schrodinger were in the mid-1920s had basically did 3 branches of quantum physics that all related to each other, but they were all very different approaches. So I introduce the wave function psi. And this basically says that if we're going to describe a particle, we are going to use this to describe it, and when it is observed, it will become a single thing. And this is the Schrodinger cat thing. The fact that you have cat in a box with a possible lethal gas released, but you don't know. So until you know whether the gas has been released or not, you have to treat the cat like it's alive and dead at the same time. And it's not until you observe it that you collapse the wave function to a single entity. It's either alive or it's dead. So the wave function is basically covering all the bases until you actually can narrow it down. This gets into what really seems like questionable reasoning. However, it seems to work. All right, so we're now gonna derive there's some markers around here somewhere. The time independent Schrodinger equation. Now, for whatever reason, using capital U to represent potential energy works fine until you get to this. At this point, textbooks decide to switch, and they'll now use capital V for potential energy. Not the electric potential that we have done in this course, but potential energy in this case. So for this, V equals potential energy. And so therefore, my total energy is equal to K plus V, capital K. I know that my kinetic energy, well, you know too, the formula for kinetic energy,
1/2 mv squared.
which is mv squared over 2, which is m squared v squared over 2m, which is just p squared over 2m. The momentum squared divided by 2 times the mass. I know that the wavelength, the de Broglie wavelength is h divided by p. I also know that if I have a function that is dependent upon kx, so if I had, let's think back to the electromagnetic wave, equals whatever my maximum value is, times the sine or cosine of kx minus omega t. It's just a classic wave equation. What is the wavelength? Not by itself.
K over M, was it? K over 2 pi? Or 2
Closer.
pi K?
2 pi over k. 2 pi divided by the wave number. Right, so I need to somehow differentiate my k's because uppercase and lowercase k's look very similar. So this is going to be equal to 2 pi over, if we're talking about a wave, over the wave number, k. So therefore, P, from this, I know that P is equal to hk over 2 pi. And if I plug that into here, I get my kinetic energy, just the different form of my kinetic energy becomes h squared k squared over 8 pi m. Nope, lost that one. So I'm squaring that, so for that part's right, so 8 pi squared. And somehow I lost, okay. Which can also be written as h bar squared k squared over 2. That's again, h over 2 pi is equal to h bar. Let's just take a simple equation here. So if psi is equal to a sine kx, I don't need the omega t because we're doing time independence. The psi dx the next derivative,
minus negative 8k squared sine kx.
which is just negative k squared times psi. And I know that k squared, well, from over here, becomes negative 2m over h bar squared times the kinetic energy times psi. Well, kinetic energy is just my total energy minus my potential energy. So K is equals my total energy minus V. So I'm going to make that substitution right there. And so I've got second derivative. So d squared psi dx squared is equal to negative 2m over h bar squared, 2m over h bar squared times E minus V psi. I'm going to multiply this coefficient over to the other side, so I get negative h bar squared over 2m d squared psi dx squared equals E psi minus V psi. Add V over to the other side, and I get negative h bar squared over 2m d squared psi dx squared plus V psi is equal to E psi. We can take it one step further, as sometimes textbooks will. If I sort of factor out, it's not officially factoring out the psi, but we're going to sort of factor out the psi and write it as negative h bar squared over 2m d squared over dx squared plus V psi is equal to E psi. This right here is an operator. It doesn't exist by itself. I can't divide both sides by side. Even though it's not done, an analog of that, if I had cosine of theta plus sine of theta, the equivalent would be to go, well, that's just cosine plus sine theta. You're not really extracting theta from the cosine and theta from the sine, you're just writing it in that form. So this is not generally considered legitimate math. However, this is generally considered legitimate math. We can take it one step further, because that's one-dimensional over there. We can make it three-dimensional. Negative h bar squared over 2m, that's the mass of the particle being described, times the nabla squared, psi plus V psi is equal to E psi. So the three-dimensional, and this is the one-dimensional Schrodinger's time-independent equation. I went to SeaWorld 20-some years ago, before the Blackfish documentary came out. And they were having a, who's smarter, the grown-ups or kids, and they showed the kid a simple math problem that he could do. And the equation that they showed to the grown-up for him to solve was the time-dependent Schrodinger equation, which frankly can't be solved without boundary conditions or a situation. So, but. Anyway. Alright, so let's actually apply this. So I have this function here. How does this help? Well, actually, we'll probably stick with the one-dimensional version of it. How do we actually find an equation to describe a particle? So we are gonna start out with the free particle. Woo! Yeah, it's not real exciting. Well, use it as a starting point anyway. No, actually, let's take a break here as I decide whether I want to do this one or not. Take 5. All right, something that I skipped over and definitely meant to do. This right here. When we talked about with the Bohr model, you excite the electrons to move to a higher level, it's unstable, so the electrons will come down, and when they do, they will emit light of a particular frequency. So if you get more energy from a photon than the electron can take, so it needs 2 units to move to the next higher level, and you send 3 units, and that's not enough to get it to a level above that, then it'll take the 2 units to move the electron to the next level, and then the other one the remaining energy will be shot off at a light at a lower frequency. That was the Compton scattering. However, if you turn this on, it's basically, I'm not sure what gas is in here right now, but we should be able to identify it. So you want to line up this little slit here with the light, and then if you look over here, so that's lined up, you look over here, you're going to see some very clear color bands next to basically a chart which tells you the wavelength in nanometers. So if you come on up and take a look at this,